Missing someone. Missing someone. Missing someone. Love with all your heart. Missing someone. Love with heart. How much you listen, and you listen, and you listen, and you listen, and you did it right from the start. And you did it right from the start. Missing someone is as normal. Missing someone and missing someone is as normal. Missing someone. Love with all your heart. Missing someone. Love with heart. Missing someone. I am sad and so low. I am sad and so low. Missing someone. Missing someone. Missing someone. Love with all your heart. Missing someone. Love with heart. How much you listen, and you listen, and you listen, and you listen, and you did it right from the start. And you did it right from the start. Missing someone is as normal. Missing someone and missing someone is as normal. Missing someone. Love with all your heart. Missing someone. Love with heart. Missing someone. Missing someone. Missing someone. Love with all your heart. Missing someone. Love with heart. How much you miss it. And you miss it. And you miss it. And you miss it. And you did it right from the start. And you did it right from the start. Missing someone is as normal. Missing someone and missing someone is as normal. Missing someone. Love with all your heart. Missing someone. Love with heart. Missing someone. Normal. I am sad and so down. I am sad and so down. Missing someone. Missing someone. Missing someone. Love with all your heart. Missing someone. Love with heart. How much you miss it. And you miss it. Missing someone. Missing someone. Missing someone. Love with all your heart. Missing someone. Love with heart. How much you miss her. And you deserve. And you deserve. And you deserve. And you did it right from the start. And you did it right from the start. Missing someone is as normal. Missing someone and missing someone is as normal. Missing someone. Love with all your heart. Missing someone. Love with heart. Missing someone. I am sad and so down. I am sad and so down. Missing someone. Missing someone. Missing someone. Love with all your heart. Missing someone. Love with heart. How much you miss her. And you deserve. And you deserve. And you deserve. And you did it right from the start. And you did it right from the start. Missing someone is as normal. Missing someone and missing someone is as normal. Missing someone. Love with all your heart. Missing someone. Missing someone. Missing someone. Love with all your heart. Missing someone. Love with heart. How much you miss her. And you deserve. And you deserve. And you deserve. And you did it right from the start. And you did it right from the start. Missing someone is as normal. Missing someone and missing someone is as normal. Missing someone. Love with all your heart. Missing someone. Love with heart. Missing someone. I am sad and so down. I am sad and so down. Missing someone. Missing someone. Missing someone. Love with all your heart. Missing someone. Love with heart.
What's up, guys and girls? Welcome to trèSci Weekly, episode 11. I'm one of your hosts, Jonathan Ullman, alongside the 64-bit hero himself, Tom K.
What's up, guys? Thanks for the intro.
Oh, thank you for being here, my friend. How are you?
Good. How are you doing, sir?
I'm on cloud nine, my friend. Yeah, it was a nice week. Had
Nice weather.
Yeah, had
Spring-like weather.
Spring break like weather.
Spring break weather.
Yeah. Yeah, had the week off from teaching, so got to spend some time with family, got to spend a little more time doing some research for the show,
Yeah, a little more relaxing of a week.
Yeah, which was great. For those of you joining us, welcome back. If you've seen this show before, if you're a first timer, welcome to trèSci Weekly. This is a video series where Tom and I like to discuss science news topics and how we feel about them. If you are coming back to the show, you'll notice we look a little bit different.
Yeah, we got all spiffy and fancy.
Yes. Want to give a huge shout out to Katie Kremens, longtime friend of the show, who has gone out of her way to make us a whole bunch of logos, cover photos, basically a huge graphics package that really makes us look 1,000 times more professional than we looked in the past. So thank you very much for that. Yeah, it looks a heck of a lot better than the garbage green and yellow thing that I kind of use as a placeholder, huh?
Yeah, we're looking legit.
We are looking legit, and so that's really awesome. If you guys take a look at our Facebook page at facebook.com/trèSci Weekly. You'll see some updated images there. Twitter.com/trèSci Weekly. We've updated the cover photo there. We've updated our YouTube channel. Finally.
Graphics, yeah.
Yep. So that's great. And last but not least, patreon.com/trèSci Weekly. This is brand new, fresh look. So basically all our social media pages that we have thus far. Speaking of Patreon,
yes, we got good news, big news.
Got a another big shout out to go to our good friend Dan Smith, who generously donated $50 to us this month. That's a huge donation. Yeah, so we really appreciate that as well. Also want to give a shout out to Tom, your mom, and your sister Karen Kea and Michelle Kea, who each have been continuously supporting us at the $10 level per month. So that is awesome. Again, we encourage you guys, if you like this content, to check out our Patreon website, which, like I said to you earlier, I want to update that a little bit to kind of give some more tiers, some more incentives, some more things that we're doing.
If you do support us, that you can get some things extra out of it that other people might not.
Right. Start setting some goals for ourselves, right? When we reach certain levels of patronage, basically, that we will start doing more things. So thank you to everybody
for all the help and support, and let's keep the trèSci dream going.
Exactly. Yeah, we're really excited now that we look more professional. We'll be much more inclined to kind of direct people to the social media pages, and we encourage you guys to do that now as well.
Yeah, share them out there. Tell the people.
Yeah, share it with everybody. All right. One last little bit of housekeeping. Speaking of doing more things, we made a Facebook event for our upcoming library program at the Carnegie Library in Patchogue, Medford. Mm-hmm. We're going to be doing an hour-long program called The Science of Stress, which you have kind of designed most of thus far. Mm-hmm. That's going to be on May 1st from 4 o'clock p.m. to 5 p.m. So if you know anybody that would be interested, we're kind of gearing it more towards middle to high school range. So if you know anybody that would be interested, direct them to our Facebook event page and have them register at the PatMed Library to sign up for that. Yep, it is free, but yeah.
Yeah, so if you're in the area, you could just stop by as well.
Yeah. So, Tom,
it's time for news.
It's time for some news. Let's get right on into it. There are 7 items on the list today. And yeah, we'll just jump right on in. So, number 1, as we mentioned on last week's episode, there was a NASA press release. So, in the press release that was live streamed on Thursday, April 13th, 2017, NASA announced new research results providing insight to #Ocean Worlds. That was kind of their thing they kept pushing. The ocean worlds were Enceladus, one of the moons of Saturn, as well as Jupiter's moon Europa. So right away, I just kind of cut myself off. Not a huge surprise there, right? We kind of predicted it would be news about these 2 particular
icy ocean worlds.
Since 2005, NASA's Cassini spacecraft has performed a series of low-altitude flybys through a plume of material that erupts from cracks in the sheet of ice covering Enceladus' subsurface ocean. By analyzing the material ejected using the ion-neutral mass spectrometer on board Cassini, a team of researchers from the Southwest Research Institute determined the presence of molecular hydrogen gas in the plume. Trace amounts of H2 gas could be an indication for a similarly observed phenomenon within the oceans on Earth, right? Sorry about that. Within the oceans on Earth. Quote, in hydrothermal systems on Earth, water reacts with rocks containing reduced iron-bearing minerals to produce molecular hydrogen. Reduced iron acts as an oxygen sink, providing sufficient reduction potential to drive the conversion of some H2O to H2. Because of rapid convective transport of fluids in these dynamic systems, hydrothermally derived H2 is far from chemical equilibrium when it mixes with oxidants in the cooler surrounding environment, end quote. All right. So, where we find these hydrothermal vents in Earth's oceans, we also find microbes feasting on the hydrogen gas byproduct as a source of chemical energy. With this finding, Enceladus has rapidly become one of the primary locations in our solar system to look for a habitable environment beyond Earth. And we can take a quick look at a video by NASA's Jet Propulsion Laboratory for more info, Tom. Do you want to chat about anything before we take a look at the video?
Yeah, just before we hop into the video, we've learned in a lot of our classes at Stony Brook about hydrothermal vents, and they bring up the point that this is sort of an extreme environment where life happens to thrive. So it's kind of counterintuitive where an extreme environment can allow a certain little niche of life to exist in this weird sort of environment. But it seems to be a consistent environment, right, on Earth. Wherever we see these smokers, you find life there.
Right.
You know, it's not like there's these random smokers and there isn't life. It almost always is a part of an ecosystem of life.
Yeah.
So it's really cool to see something very similar mechanism on these moons of faraway planets that have the same sort of chemistry in water, right? So the liquid water in that chemistry, that's really the golden ticket that we're looking for, right?
Yeah. So really exciting because, this now becomes the best case of where we might see a similar sort of recipe or ingredients list for life as we know it. So, now all we have to do is really kind of pull back the curtain and take a look, see what's there. So let's go to that video. Yeah, let's check out that video. Kyle, as always, let me know when to hit the old play button there. Okay.
This is Enceladus.
Correct. And this is the Cassini spacecraft that we covered last week. That is kind of
that's
at the end of
those
its
flybys, and will eventually end up in Saturn.
The instrument acts like a human nose, analyzing the smell, so to speak, or the composition of the gases in the environment. There was a significant amount of molecular hydrogen. The existence of molecular hydrogen, at least within the Earth's ocean system, is like a food source. It's candy for microbes. They eat the hydrogen, they turn it into methane. And with our findings, we were able to not only find out that there was H2 in the system, but to examine the chemistry that's associated with that process of taking hydrogen and turning it into methane. Here on Earth, the hydrothermal systems, known as white smokers, have water-rock interactions that lead to the release of molecular hydrogen in a similar fashion to apparently what's going on at Enceladus.
The three ingredients.
This is just the final step that shows that
the
there's
right
molecular hydrogen being produced by these same hydrothermal processes, and that molecular hydrogen has the chemical energy to support microbial systems in the interior ocean. It's not demonstration of finding life, but it shows the potential for the existence of life in this interior ocean.
Yeah,
very cool.
Yeah, pretty interesting stuff there.
Yeah, so I think we were in college when they first discovered that there was microbial life in these hydrothermal vents. Am I right about that?
I'm not sure.
That's the first time I remember hearing about it, but that just might be because that's when I first learned about it. But that was a huge kind of unbelievable thing, right? We never really understood or we never really thought that life could exist without sunlight, right?
Yeah.
That the sun provides that source of energy for life to kind of take hold. And here we have no sunlight at the bottom of the ocean, but chemical reactions.
Yeah, it's all the chemical energy.
Yeah, and you can use that sort of fuel as food, right? As an energy source for life to kind of take hold. So
yeah, so it just so happens that like the physics at the bottom of the ocean allows for these chemicals to happen on the bottom of the ocean. It just happens to be where they are. So it seems like a weird place for life, but I mean, it's at the bottom of the ocean.
Yeah.
That's where the stuff comes out. So that's where the life grows.
Yeah.
So it started from the bottom,
Now we're here.
Yeah, that's how it happens. All right.
So moving on, that wasn't the only announcement. In addition, NASA announced some similar findings on Jupiter's moon Europa, which also is believed to have a salty subsurface ocean covered by a layer of ice. While the Europa data is more speculative than conclusive, it is still nonetheless exciting. NASA's Hubble Space Telescope was used to observe a very similar plume of material being ejected twice from the same location on the moon's surface over a span of 2 years. The first observation was made in 2014 and the second in 2016. The plume area corresponds to a warm region on Europa's surface that was thermally identified by the Galileo mission that visited the Jovian system back in the late 90s and early 2000s. While more research is needed to identify if the plumes and the thermal anomaly are indeed linked, the evidence pointing to a confirmed plume event has heavy implications for NASA's upcoming Europa Clipper mission. Scheduled to launch sometime in the 2020s, the Europa Clipper mission will likely replicate what Cassini did for Enceladus, a flyby through the ejected material of the plume for chemical analysis, as well as further targeted research detailing Europa's potential for habitability. We can take a look at one more video by NASA's Goddard Space Flight Center starring Katrina Jackson, which provides some further insight. Tom, did you see this as well?
Yes.
Of course you did.
This is a so now we're talking about Europa.
Right. So Europa, one of the 4 Galilean moons, one of the kind of the larger moons that Jupiter has. This one...
So one moon on Jupiter, one on Saturn, but they seem to have pretty similar conditions of ice, liquid water, and then possible fuel for life within that liquid water.
Exactly.
So pretty similar cases for their life.
Yeah. So now, this kind of... I like the flow that they had, that NASA's press conference had, where it says, hey, the Cassini mission that's been studying Saturn and Enceladus is coming to a close. Here's one of the most exciting things that we learned from it, which is the existence of hydrogen, molecular hydrogen gas coming from this plume. Then they segue into an observation that the Hubble Space Telescope made that kind of points to the fact that this might be happening on Jupiter's moon Europa also.
But we would need...
We need to send now a dedicated spacecraft mission to further analyze those results, right?
The same way we did with Cassini on Saturn.
Exactly. So NASA...
And yeah, Cassini, like we mentioned, that one's coming to an end.
Right.
So going into a new chapter of research. Right?
And NASA's already been planning a Europa Clipper mission, right? And this is what NASA is very good at, is taking exciting data and findings and sort of segueing the future missions.
A direction for research.
Right? And it gets everybody kind of hyped. It gets me hyped.
Yeah.
So let's take a look at that other video. Again, Kyle, if you would be so kind as to let me know.
Hubble has found even more evidence of water vapor plumes on the ocean world Europa. Last September, we announced that the Hubble Space Telescope had taken multiple images of what could be water vapor plumes on Jupiter's moon Europa, an icy world that's thought to have a subsurface global ocean of water. That same team of astronomers has now taken additional ultraviolet images of probable plumes on this icy moon. While these plumes seem intermittent, they appear to have repeated in the same location. Pieces of the puzzle of what's going on with Europa are continuing to come together.
Inconclusive to say
when the
exactly
Galileo
what it is,
spacecraft was orbiting Jupiter in the late 90s and early 2000s, it gathered data to build a thermal map of Europa, and it appears the water vapor plumes Hubble is observing correspond with a relatively warm region on Europa's southern surface about 200 miles across. This thermal anomaly the Galileo spacecraft observed suggested geologic activity was happening in this location, a conclusion now further supported by Hubble's recent observations of water vapor plumes. This phenomenon may be similar to what the Cassini spacecraft has seen at Saturn's moon Enceladus, where there are also water vapor plumes associated with warm regions on the moon's surface. The warm spot on Europa has a couple possible explanations. Perhaps this location is warmed by liquid water a mile or so under the surface, pushing up through the cracks in the ice. Or perhaps the fine mist that's falling from the water vapor plume changes the structure of the surface ice grains, allowing them to retain heat longer than the surrounding landscape. Now that Hubble has shown Europa probably has water vapor plumes associated with warm spots on its surface, this information will be used for planning NASA's upcoming Europa Clipper mission. Europa Clipper will be able to take up-close observations of these probable plumes Hubble identified, and will be equipped with instruments that can detect any additional warm spots and water vapor plumes. This will provide insight into Europa's chemistry, geology, and potential conditions for harboring alien life.
All right. Cool. So, we talked a little bit last week about NASA press conferences in general, Tom, right?
Yeah.
Because they had the announcement back in February about the TRAPPIST-1 system, all those terrestrial type planets that were orbiting an M-type dwarf star. And then last week we kind of got some bad news in regards
some counter evidence. Yeah.
In regards to that, whether or not those rocky planets could really support life due to the frequent flaring that star produces,
and how close the planets were to the star, and that those flares would be too disruptive for life to occur, or for an atmosphere to be able to be on those planets.
Right.
That's what we believe. So yeah, that system was looking less and less likely for life, even though that was only just one study. It just seemed a little bit further of a stretch. So now moving on to the next press conference, now it's another way to bring you back to, well, here's still good ways to look at life right in our own solar system.
Yeah, so I think that's great,
a good idea
to kind of bring it back home a little bit more, instead of doing a press conference that would maybe focus on another exoplanet system. I think it's important to shift the focus. I would have liked to see, I liked what I saw here. I would have liked to see some more news about Mars maybe, but I think focusing back in on our own solar system makes a lot of sense for the follow-up press conference, although I'm sure many people did not hear about the flaring report that we talked about last week. So in the eye of most people, it's probably just all good news, right? Yeah. But nonetheless, this is really interesting. Did you see when they, during the press conference, when they did kind of the Ask NASA hashtag for people to kind of ask questions directly, and the one person said, well, now that we have sort of a way to calculate how much molecular hydrogen gas is coming out of Enceladus, we could basically do a calorie count, right, for how much food supply there would be for the microbial life. And somebody asked, did you do it? Like, how many calories were there? And of course, in typical scientist nature, they responded with, there's enough to equate to 300 pizzas, right? Like,
yeah.
Instead of giving the number. But I like that. I liked how kind of funny they could be with it. So,
yeah, I did like that also.
Job well done. And we shall see what the future holds with these new missions, and basically if we ever get to kind of dig below the ice and see what's down there.
Be exciting.
Definitely. Moving on. Quick headline grab, right? Just to follow up on the NASA story. Abby Tabor of NASA's Ames Research Center writes, "From orbit to core, scientific synergy between NASA and the U.S. Geological Survey." Quote, "Building on a 50-year-old partnership, NASA and the U.S. Geological Survey, or the USGS, are expanding their cooperation with the relocation of one of the largest USGS science groups in the western United States to the NASA Ames Research Center campus in Silicon Valley. Both agencies are looking forward to reinforcing their close partnerships to study our planet from orbit to core. The possibilities enabled by bringing together scientists and engineers from the nation's top agencies for Earth, space, and aeronautic sciences are enormous. Over the next 5 years, more than 300 USGS employees will make the move several miles south in Silicon Valley from their current Menlo Park campus to the nearby NASA Research Park. The idea for NASA and the USGS to co-locate has been in the works for several years. On November 1st, 2016, Ames Research Center Director Eugene Tu and USGS Pacific Regional Director Mark Sogi signed an agreement to pursue the move officially. The proximity of the two research communities will enhance their collaboration, fueling research on natural hazards, water resources, atmospheric science, climate change, and more. The move also will allow the USGS to invest more funding in science that otherwise would have been spent on San Francisco Bay Area rent. End quote, Tom. And I know that San Francisco Bay Area rents can get pretty pricey.
Yes, it can.
What do you think about this?
So, this we were talking about relates back to what we were saying, that with a lot of these cuts out there, there's a lot of look to make things more concise, to make things streamlined a little bit. And this seems like a way to streamline these two organizations together so that they can get done what they need to get done together through collaboration, which they probably wouldn't be able to on their own with current funding coming up.
Right.
So it makes a lot of good sense, as well as the practical reason to move away from things that aren't practical, like the rent in the area.
Yeah.
So it seems smart on a whole bunch of levels.
It's a no-brainer,
Yeah.
right? I mean, we saw with the proposed budget that was released last month, NASA was having not as much of a budget cut, but more of a refocusing to divert attention away from earth science studies and more into kind of, studying the cosmos abroad, right?
So, but they still have a lot of infrastructure for studying the Earth.
Exactly.
So bringing in people from the United States Geological Survey kind of fills in that void that would be left by that refocus of where they're trying to do their research.
Yeah.
So it kind of makes sense to bring those group in.
Yeah.
And it seems like we can still get a lot of good research being done. Like, they're finding ways to do it. They're not giving up.
No, they're not giving up. And honestly, this will probably expedite things, right? This will make things more efficient, and collaboration between groups that might not have otherwise collaborated
as much. Yeah.
So I think this is really, really a home run situation, actually, Tom. So just wanted to throw that in there.
I agree. And I like USGS as well as NASA, so seeing them team up is good.
Yeah. What do you think? You think eventually these two agencies merge into one?
I don't know.
I don't know either.
Say, but
yeah. I kind of hope not, but
I think they do enough things differently, uniquely enough where they will stay their own organizations.
Yeah. We'll see. Number 3.
New topic.
No more space news, actually, for the rest of the show, believe it or not. Number 3. An energy-favorable device that harvests water from relatively dry air has been created and detailed in a new paper published by Hyunyo Kim and colleagues in the journal Science on April 13th, 2017.
So, as soon as I started this in the beginning, they made it abundantly clear that it can be taken out of dry air.
Right.
So that's their whole point. We're going to explain kind of how they do it, but they're saying now we have a device where we can get water out of dry air, which was never possible before.
Right. So air, largely made up of nitrogen, oxygen, water vapor, and carbon dioxide.
Small percentage. Even when it is pretty humid, water vapor is a pretty small percentage of the gas in the air.
Right. But there is water vapor, water gas in our air, and this will be a really useful tool, it seems like, to kind of extract it out of the air and
allow us to drink that moisture.
Make it potable, as they say. The device, which is about the size of a drinking glass at 7 centimeters by 7 centimeters by 4.5 centimeters, makes use of a porous metal organic framework, or MOF, that captures water vapor directly from the atmosphere via adsorption. Quote, "We demonstrate water harvesting in ambient air with low relative humidity, typical of the levels found in most dry regions of the world, down to relative humidities of 20%, end quote. This is a huge step forward from similar devices that can perform the same adsorption processes, but are limited to doing so in atmospheric environments with very high relative humidity, where the effects are really quite meaningless. In addition, the device is able to deliver liquid water, approximately 2.8 liters for every 1 kilogram of the MOF used, by using sunlight to generate, quote, a low-grade heat-driven vapor desorption process, end quote. The use of solar energy as a passive energy source is ideal since many arid environments with low relative humidity tend to have an abundance of sunlight, right?
That is very true.
Deserts that are dry tend to have lots of sun. The particular metal organic framework used for the device is known as MOF 801, a microcrystalline powder containing zirconium-based compound clusters that is coupled with copper foam to produce pores with exactly the right size for water vapor extraction. Quote, MOF 801 has several advantages in that it has 1. Well-studied water adsorption behavior on a molecular level. 2. Good performance driven by aggregation of water molecules into clusters within the pores of the MOF. 3. Exceptional stability and recycling. And 4. Wide availability and low cost of its constituents. End quote.
So they're trying to make it seem pretty practical.
And marketable. Which I think is important. The researchers are optimistic that the prototype device they have developed can be upscaled to larger infrastructures, which may go on to help solving water shortages across the globe.
So they're saying it can kind of be extrapolated to a larger scale.
Right. So theirs
was about maybe like a community or something.
Correct. Theirs is about yay big, but they say, if you just...
The principle applies, right. It's a scale.
You just make it bigger, then you have a bigger, basically, water collection device. The image credit, of course, goes to Kim et al., the people that wrote the paper. This I thought was really interesting because I think that they're making all the necessary points that this is a marketable device, right? And you can market it not just to desert communities or whatever, but to people who like hiking. If they had a little device that they could leave out overnight while they're camping just to collect water straight from the atmosphere, why wouldn't you do that? That's a way more efficient way. Yeah.
If it was practical and not too expensive,
right?
It could be a tool. And we were kind of joking around. No one's gonna get stranded anymore. So how are we gonna write books about all the people surviving on islands?
Yeah.
When they have their handy dandy device to get their water.
Yeah.
But all jokes aside, it seems like a really pretty cool piece of technology, as well as a good process in which they've learned to extract water using these materials. So, like they're saying, it can be extrapolated to a larger scale, where if we had large water shortages, I think these sort of technologies will become extremely important as the future goes on, because there's going to be water crises around the world. It's already happening in various countries.
Absolutely.
So this could be a game changer in the water.
Yeah. What do you think? You think NASA buys into this, buys this device, sends it over to Enceladus in Europa where the plumes are? It's taking the water vapor out of the atmosphere there and creating drinkable water for future researchers?
Imagine we just extracted all of the water from a moon on another planet.
It's possible.
Definitely interesting to think about.
Yeah, right? All right, moving on. Number 4. Tsunamis may gain a significant amount of energy via lateral horizontal motions, a new study by Yuhei Tony Song, Ali Motat, and Solomon Yim suggests. Tsunamis are ultimately caused by the subduction of an oceanic plate below a continental plate. As the oceanic plate slides underneath, the continental plate bends with it until it reaches a snapping point.
Yeah, so the oceanic plate is more dense and heavier, right? So that one is the one that has to go below it. And then as it's going underneath it, it's saying that it reaches a snapping point on the continental plate. And once it does that, that's when you get a quick sudden movement, right?
Right.
When it reaches that breaking point. All the force is built up. It's like, waiting to go. And then that snap, there's a rebound effect, right?
Yeah.
So same thing as if you were in your pool with a boogie board and went slam down, you see a resulting wave.
Yeah. The slip releases a tremendous amount of energy in the form of an earthquake, and the resulting snap upward of the continental plate forces the large volume of ocean water lying on top to swell outward as an enormous wave, exactly like we just said. Traditionally, scientists try to correlate the size of a tsunami wave with the amount of vertical displacement of the snapped plate, but those correlations sometimes have discrepancies, as is the case with the 2011 Tohoku earthquake, which produced a devastating tsunami that struck the coast of Japan. Quote, "The vertical seafloor uplift was only 3 to 5 meters, too small to account for the resultant tsunami. Surprisingly, the horizontal displacement was undeniably larger than anyone's expectations. About 60 meters at the frontal wedge of the fault plate, the largest slip ever recorded by in situ instruments." End quote.
So the way they used to do it, they always just correlated with how big is the drop, the vertical drop. And it worked for most cases, but when you get a case like this where there is that horizontal motion, that rule really doesn't apply anymore.
Right.
So where it worked to correlate a long time, they had a pretty good idea of what tsunamis were doing. But now understanding this, you'll really get a better understanding of what kind of tsunamis you're going to get with what kind of fault movement. Pretty cool.
Song Motat and Yim conducted a number of experiments using computer simulations as well as testing waves and flumes generated with a paddle. Ultimately, the study argues that the total energy of a tsunami must account for the horizontal displacement of sloped terrain located underwater, as this helps propel water forward, thus growing the size of the wave, right? So not just vertical motion, but horizontal sloped motion, right? If here's a slope, something like that.
To push all the water along, as well as the drop that happens.
Right. The researchers hope to increase the amount of predictive power scientists have when assessing tsunamis from future earthquakes. For reference, here's a video by Oregon State University showing off one of the flumes used to generate waves for tsunami research. I should note, too, that a couple of the researchers involved with this are from Oregon State University, so I imagine that this is probably the same flume that they used, although I don't know for sure. But nonetheless, I wanted to show you guys this video because it's just kind of cool to see how they do tsunami testing. So Kyle, let me know when to hit play on that bad boy. So this is a flume, Tom.
That's what it's called. The long tube is a flume.
Yep.
So you'll be able to see why they're screaming in the background.
Yeah, there's a bunch of these.
It's pretty cool.
That's how they generate waves.
How would you know?
So it's just a laboratory homemade mini tsunami.
Yeah.
We were joking around before that it's in a similar manner how they make the waves in a wave pool or something.
Yep.
Just displacing the water correctly. And then having a slope to allow the wave to build up.
Yeah, you'll see it better, I think, here. Bet you Ryan Nash wants to take his surfboard out there.
So now they're just showing multiple waves, like wave after wave.
There we go.
So it's just the movement of that allows the water to rise and fall, and then it pushes the wave out. Pretty cool. So they correlate the amount that moves to the size of that wave, and they try and create a model system to then extrapolate to the big real world picture.
Yep.
Very cool.
Very cool. Very awesome.
I'd like to get into some tsunami research one day, maybe.
Yeah.
Pretty cool job.
It is. They have another one of these kind of wave pools at Oregon State, and it's kind of a more open thing, not a flume, but an open pool. And they showed that if you have a wave that hits, just like the tsunami wave hit the coast of Japan, along the outside, right, the water motion creates those cyclones, right? And that's where all that footage back when that happened in 2011 of those massive boats getting sucked down in this like swirling drain, that's what that's from, right? Is that creates kind of this weird circling motion. So I thought that was really interesting too, but kind of not applicable to this exact same study here.
Mm-hmm. In the chat, a few people making jokes about Split Splash in Oregon.
Yeah.
It's funny.
Split Splash is awesome. We have to go this summer. Number 5. The physics of shoelaces, Tom, becoming untied.
Have finally been
finally been detailed and documented by a team of mechanical engineers at the University of California at Berkeley.
So now we know when you're walking, the physics behind why your shoelaces become untied.
Surprisingly,
So,
this has never been really detailed.
No one's ever known, huh?
Yeah.
Let's figure it out.
Christopher A. Daly Diamond, Christine E. Gregg, and Oliver M. O'Reilly report that there are actually 2 contributing factors that lead to laces coming loose. First, as a shoe repeatedly makes an impact with the ground or floor during an individual step, the knot will begin to loosen.
So just by the impact on the ground, that's enough to loosen it up a little bit.
Secondly, as the individual walks or runs forward, the free ends of the laces will experience a swinging motion, which continuously causes them to slip out of the already loosened knot.
So that swinging comes from like inertia, right? As you're walking, your shoelaces are moving forward, and then they begin to sway back and forth.
Yep, something like so. Quote, this leads to eventual runaway untangling of the knot. As demonstrated using slow motion video footage and a series of experiments, the failure of the knot happens in a matter of seconds, often without warning, and is catastrophic.
It's catastrophic. Leads to your shoe becoming untied.
We can take a look at some of the slow motion footage via Daily Diamond, Gregg, and O'Reilly's report. So, I don't think that there's any sound actually for this one. Let's see here. Kyle, give me the go ahead. All right. So we get the slow motion footage.
Ooh, they got those fancy shoes.
Yeah, the toe shoes.
When those first came out, everyone was trying to buy those.
So take a look at the knot here, right? You'll see.
So you can see the shoelaces going back and forth, and then the pounding,
the impact
looses the knot,
right?
And then that back and forth motion just eventually allows them to become untied. So this just pops into my head right now. So I used to work at a camp with a whole bunch of little kids whose shoes were always untied, and some of the same kids' shoes would always become untied. And now I was just thinking, is it the material of their shoelaces, right? Is it less friction in their shoelaces where this same mechanism would be happening to everybody's shoes, but if it's a material that has less friction, you might be able to untie your shoes quicker. And that's why Jimmy's shoes might be always untied from every activity to the next one.
Absolutely.
I was just thinking that might be the case.
It absolutely might be. This particular study did not
test
different materials,
laces,
right? Yeah. So that was
just
not
like the general physics behind how the lace becomes untied.
Right.
Gotcha.
But yeah, I mean, almost certainly, right? Different frictional forces would cause that loosening to happen easier upon the same number of impacts, right? So here we go. We're really starting to loosen up.
And here's the catastrophic effect of losing your shoes.
It's over.
And then your knot's gone.
And it's over.
But they mentioned in the article as well that it would depend on what kind of knot you tie in your shoe, right?
Correct. So we'll get to that. There are definitely...
So there's better knots than others for shoe tying. Cool.
20 more seconds left here. I don't know if the other shoe comes undone also. Guess we'll see. Closing moments.
This reminds me that you can also film in slow-mo on your iPhone now. They added that in.
Yes. We're going to have to do some experiments of our own.
Karen Riley says, I always tie a double bow and it never comes undone. That might be a good way to tie your shoes.
There you go. All right. So... while slow-motion footage helped provide real-world observational data, the researchers also used a more controlled experimental setup consisting of a pendulum that would make precisely measured impacts with an accelerometer and an impact surface. So Kyle, if you are ready and you want to shoot over to that second video, we can take a look at that. All right.
So what are we looking at in this one?
So now this is them kind of testing a controlled model where now there's an exact measurable frequency, an exact measurable force of impact.
And how long it takes for that knot to come out.
Exactly.
It's just a more well-designed experiment without using actual shoes.
Right, you can make the measurements with certain criteria much easier than having a person run on a treadmill, right? Because what if they get tired? You know? So we don't have to watch this whole thing. It's 2 minutes long.
It's
and
like bang your head against the wall.
Yeah.
You get the idea.
I can, spoiler alert, the knot comes undone. So we'll click out of that and we'll finish up the kind of the write-up here. Although certain variables such as shoelace material were not explicitly tested in this study, the researchers concluded that weak knots, such as granny knots, are much more likely to fail faster and more frequently than a strong knot, such as a square knot. So Tom, do you know how you tie your shoes? How do you do it typically?
I do it with you make one loop and then I go around it and then just tie it up.
Sweet. So that's a square knot. That's exactly what I do too. So you and I, we tie our shoes with the stronger of the two different knot types.
And in the chat, they're making some funny good points. That SpongeBob taught them loop-de-loop and pull, and now your shoes are looking cool.
Yeah.
So is that a good way to tie your shoes?
So I think that is more the granny knot. Yeah.
So you're like, it may be an easy way to teach a kid, right, with the bunny ears or the two loops, but that is technically a weaker knot, and your shoes will become untied easier.
Yeah.
But as Chris mentioned in the chat that I thought was funny, Velcro is greater than laces.
That is true. Velcro is a NASA developed product.
And then you put it right on the shoes.
Velcro is so funny to me, man. It's just literally little hooks
that go into the other stuff.
That go into this mesh of like little plastic loops. But over time, right? Every time you unvelcro, you snap all the little loops there.
So it gets worse over time as well. But
yeah. But it's still funny. It's still fascinating.
A lot of good points.
Number 6. European eels, Anguilla. Tom. I always love when the scientific name of a species is the name twice, right?
The genus and species.
Yeah. This Anguilla sometimes reminds me of Shakira. I don't know why. Anyways, European eels use variations in the Earth's magnetic fields in order to gain a sense of direction along their migration routes, according to a study by Lewis Naisbitt Jones and colleagues. The eels hatch and begin their lives in the Sargasso Sea, an area in the North Atlantic Ocean that is actually the only sea bounded by ocean currents on all sides rather than land. Right? So there's actually a sea in the Atlantic Ocean. Right.
That's interesting.
Juvenile eels then migrate to the northeast, where they spend most of their adult lives living in freshwater habitats in Europe or North Africa. Finally, the eels eventually migrate back to the Sargasso Sea, where they spawn and live out their remaining days. By performing a quote-unquote magnetic displacement experiment, the researchers were able to make sense of how the juvenile eels determine which direction to swim toward. Quote, "We observed a significant difference in the orientation of eels in the 4 magnetic fields, providing the first demonstration that eels use geomagnetic map information to orient. A field corresponding to the Sargasso Sea breeding grounds elicited southwestward orientation, while a field from the northwest Atlantic elicited northeastward orientation. A magnetic field from the northern mid-Atlantic and the ambient field at the test site elicited orientation indistinguishable from random," end quote. So I'm going to bring up the image here on my end. Kyle, do we have the image still up there? Cool.
Yes,
so you can see letter A, right? That's indicating the Sargasso Sea magnetic field. They're kind of replicating what the Earth's magnetic field would be like at the Sargasso Sea. They let all these kind of baby eels loose, and they see a stronger orientation for them to swim to the southwest, right, than in any other direction. If they move up to letter B and they replicate the magnetic field at this area, they let all the eels loose, they start to see actually a northeastern general trend. Right?
So they know where to go just based upon the geomagnetism.
Right. For letter C and D, there's kind of no real distinguishable direction, and they think that as they get closer and closer to where they're supposed to end up with their migration,
they don't need
it doesn't matter anymore, right?
Yeah, they don't need as much guidance to get there.
Now, you might think, Tom, a southwestward orientation from the Sargasso Sea would be counterproductive if the eels want to migrate towards Europe, right?
That's true.
But the researchers believe the eels make use of the energetically favorable currents of the Gulf Stream, so heading southwest from the Sargasso Sea allows them to ride the current faster, right?
So they're not trying to go directly there. They're hopping along the current to get swooped around.
Brilliant. Since eels are not the only species to make use of a magnetic map for migratory purposes, sea turtles, salmon, and trout have reportedly shown similar behavior, the researchers suggest that the mechanism may result from one of two evolutionary scenarios. Quote, the phylogenetic diversity of animals that derive positional information from the geomagnetic field, including those undertaking shorter migrations, suggests that the ability to use a magnetic map is either deeply conserved or has evolved multiple times, end quote. Image credit goes to Naisbitt Jones et al. For that graphic. I really thought that last kind of quote there was the most interesting piece of this.
That's what stood out to me as well, because it's kind of cool. Like, we know that things have used the magnetic field in the past for guidance, like we know in turtles and other things, but it's cool to think, how did they come about being able to do that? And they mentioned that it's either this deep-rooted thing that animals have done that gets passed on, or is it a separate way to learn how to use a magnetic field that has evolved multiple times? I don't think either one stands out to me as being a lot more plausible than the other, but it's cool to see animals being so in tune with nature, I guess.
Yeah.
Because, a magnetic field would be something you as a human would never try and use without a device, right? You can't sense it, but it's cool how these animals develop this way of travel.
Yeah.
It's something that seems almost invisible and non-tangential, but its effects and its strength, I guess, is able to be determined by these animals, and then they use it to navigate.
Yeah.
So pretty amazing stuff.
In my mind, it's a sense, right?
It's a new sense.
Right. It's like our sense of sight or our sense of smell. These animals have a sense of position because they have some body function that measures the strength of Earth's magnetic field at different points on the planet.
And even if they can't measure it exactly, know the strength of it in every direction, they have a general idea of the way it's trending.
Right.
They don't know the exact amplitude or whatever, but they know that the orientation of it, and they sort of follow that along.
Now, what do you think? Do you think that as humans, do we have any sense, not hope, but any kind of hidden sense of being able to feel the Earth's magnetic field ourselves, or not?
I think only when you get the spins.
Maybe. Maybe.
But yeah, kind of a cool question to think about.
Right? Do those people that are directionally savvy, do they have maybe this hidden sixth sense that we just don't know?
Might be a little bit of a stretch.
Yeah, it might be a little bit of a stretch.
But I know what you're saying.
Yeah, could be. Number 7, Tom. The Clovis people, a culture of early North Americans who emerged at the end of the last glacial period, are best known and identified by their distinct stone tools and weaponry. By chipping off flakes at the base of stone points, the Clovis people created what are known as fluted points. In a recent study by Caitlin A. Thomas and colleagues, replica fluted Clovis points were stress tested to see if there are any mechanical benefits to the ancient technique. Quote, we found evidence that the fluted point base acts as a shock absorber, increasing point robustness and ability to withstand physical stress via stress redistribution and damage relocation, end quote.
So I would go out on a limb to say that they didn't know the physics behind making a fluted point.
Probably not.
But somehow they discovered that, if you make it, the groove there in the back, it doesn't crack as much. They somehow learned that, and that's what they put in a lot of their arrow points.
It's pretty easy when, I guess, the hunter that doesn't have their spear tip broken and get eaten by the mountain lion can go on to show the other hunters, hey, I designed it this way. It just happened to look like so. By redistributing pressure away from the point and back toward the base, fluted Clovis points are less likely to break, thus increasing the hunter's weapon durability. The researchers argued this would be a practical benefit, especially for a group of people who were hunting in a largely unexplored environment, having recently crossed into North America via a land bridge from Asia. Image credit goes to the American Society for Amateur Archaeology, Tom, and we don't really cover a lot of archaeology on this show.
No,
but
I like that we talk about the Clovis people, because for me it's so interesting to think that a group of people just walked over this little land bridge from Asia, Russia, Siberian area, and just walked right over to this whole mega expanse of land with pretty unprepared knowledge and wherewithal of what they're going to get themselves into.
Oh yeah, totally.
So a lot of cool things to look about. If you're looking to research something more, I would recommend the Clovis people, because it's a cool part of our history that we don't really think about.
Definitely.
But cool stuff.
Yeah, I will provide a link to the American Society for Amateur Archaeology, where I snagged that photo from, because there was a whole write-up on different tools and different ideas on how the Clovis people might have used them. I really wanted to throw this story in there because I thought it would be a nice lead-in for Tom's Corner this week. You had mentioned to me earlier on in the week what you wanted the topic to be this week. And so the physics of kind of an ancient civilization's weaponry goes hand in hand with what you wanted to talk about this week, Tom.
Yes. So yeah, it's kind of is an interesting segue where we look at an ancient culture and they found a better way to make a weapon. And now, as a lot of time goes on, a lot of technology goes by, we found some pretty innovative and interesting ways to use our own weaponry. Mm-hmm. So I wanted to go over what exactly happened and the physics behind the MOAB bomb, or the mother of all bombs. Hold on, let me bring this up. So they call it the nickname, the mother of all bombs, but MOAB actually stands for a massive ordnance air blast bomb, and that was the type of bomb that we used to target the ISIS fighters in the tunnels on last Thursday in the Akin district of Afghanistan's Nangarhar province. I don't know if I said that right.
Yeah, I don't know if I pronounced most of the things on this show correctly. Probably not.
But, quote, in the article, they said it never actually struck the ground. So that's what makes this bomb kind of interesting. Mm-hmm. It's an air blast bomb because they call it an air blast because it detonates in the air. And that blast, when you have something going into the ground, a lot of the energy gets distributed into the actual ground. The point of this one is to explode above the surface, where that energy can then radiate outward on the surface where you want your destruction to be, basically.
Right.
So, go through it a little bit more. A massive crunch of air pressure is created as the bomb is detonated above the surface, so the majority of the energy can disperse horizontally, enabling the bomb to cause more destruction. So, the massive crunch of air pressure is created by the nearly 22,000-pound MOAB. It would have wiped out anybody in the vicinity and certainly sent a clear signal that the Trump administration is willing to use unprecedented force, because this is the first time that we used a weapon like this in the actual battlefield. Mm-hmm. Which was, I guess, kind of shockingly big news that I don't think was made as much of a hoopla about, you know?
Yeah.
They kind of just reported that we did it and that was it, even though it's a tremendous display of force.
People
right?
were talking about it, but yeah, I don't think the gravity of what we did was really kind of put out there. You know, so it's really interesting that we live in a world where weapon design has just come so far, right? And it's always coming further and further and further. I mean, if we compare the Clovis people, their weapon design worked for what they were doing, that helped them kind of take over and really establish themselves in North America for the first time. And now in North America, we grew up in an era of time where this arms race has gotten out of control, where all of these bombs and these warheads and these payloads and these nuclear weapons and chemical weapons have been designed, and people have access to them. And what do you do now? You just have to have the biggest, best one, because if you don't, then it can be used against you. Right, and this is kind of where we're at now. So I'll let you go ahead and finish up.
Sure. And then, so I have a quote saying that. Here we go. Where's the quote? So it uses something called a, quote, proximity fuse on its nose that ignites the warhead when it reaches an altitude, which can be anywhere between 50 and 1,000 feet above the surface of the ground. So they have a GPS guided system to it, so it knows exactly how high it is above the surface to set off that proximity fuse to blow it up before it impacts.
Right.
So, quote, an air blast bomb doesn't throw out a lot of fragmentation like you'd expect from a normal bomb. It's all blast overpressure, which can blow down trees and use trees themselves as the fragmentation. So they're not really looking for like the shrapnel of the actual bomb to like explode out to hurt the people. It's this huge blast of pressure horizontally that can even throw trees and things and be debris as weapons.
Wow.
But the most interesting part is here as we keep reading on. It says, quote, that the type of bomb wouldn't work well, for example, to destroy tanks, although the overpressure would kill the people inside them. You'd overpressure the people hiding in the caves there. You'd never find them. It just blows your lungs out of your mouth. It kind of turns you inside out, end quote.
Wow.
From a retired U.S. military officer. So that's the way he describes what the bomb would do to a person. You never find them. It just blows your lungs out of your mouth. It kind of turns you inside out. And then just to finish up, the use of air blast bombs in Afghanistan dates back to the beginning of the U.S. military's arrival following the 9/11 attacks.
Mm-hmm.
This is when these sort of weapons were first being used, and this was just another unprecedented MOAB bomb that they use in this particular case.
Yeah, I think it was, if I remember correctly, I think I read that it was 9 days after we developed these types of bombs we went into
yes,
Afghanistan. So not a coincidence there. Hey, we have this great designed weapon that can totally eradicate the people that live in the cave systems that they've built here. Let's go in now.
Do it.
Yeah, let's do it.
Let's go for it.
So, pretty crazy stuff, Tom.
Yeah, it makes a huge statement, right? Like, there was a joke in the chat that you need a kill streak, because I remember a lot of people first heard MOAB in a Call of Duty video game.
Mm-hmm.
That's what they use it. They use MOAB as the mother of all bombs. That's sort of, it's in like the lore of society, right? And it also makes a giant mushroom cloud like a mini nuclear missile would.
Right.
It makes the same sort of thing that you can see from miles away. So not only is it extremely powerful that it would absolutely destroy all the people that would be there, it is an extremely impressive display of force and power.
Yeah, it's a demoralizer also, right? So people that see that in the distance,
there's no way we're coming back from that.
Right.
You know, we don't want any other countermeasures. I think that's the point of this. So as crazy and as wild as this bomb was, I think in the eyes of the people who did this, it was a successful mission for what they set out to do.
Yeah.
Not saying that one way or another it's a good thing to bomb people, but I'm saying that the physics of this bomb worked exactly the way they intended it to.
Yeah. So
and to close it out, we actually have a quick video that I wanted to show to
sure. Yeah, let's cue it up
to show what it looked like. And this was actually, I saw it on the Twitter of the Department of Defense.
Yeah, go figure.
That's where I saw the video first. So if you want to cue it up,
I actually don't have it on my list here, but
okay,
if you have it,
I do have it. Yep.
Cool. We'll watch it on yours then.
All right. What? I think Kyle's bringing it up for us now. Don't rant on politics. Keep the focus on science.
So here we go.
This comes, directly from the Department of Defense. And as you see it, it instantly expands outward the way they wanted it to. And this is in the infrared, so you can see the mushroom cloud from the explosion in the black there.
Right. So, as you said, Tom, this is a kind of a triumph for physics, right?
I mean, it works perfectly as intended, as horrible as it is to what it does when it actually explodes. But yeah, it did its job.
Yeah. There is this kind of torn nature to this, right? Where as somebody who studied physics has been going into weapons development, as I mentioned, forever, since the beginning of mankind. And while I don't like the idea of using it to eradicate other humans and cultures and belief systems, it is a necessary part of the world we live in. Because if we don't have that power, then others will just do the same to us, right? It's unfortunate, but that's kind of the way the world is right now.
Yeah,
right?
It makes you take a realistic look at the history of society itself and realize it goes from one war to the next, and that's kind of how you tell the story of human history, right?
Yeah.
You go from one war to the next, and as it develops and how it all interacts, that's kind of how it works. And like you said, whoever is sort of on the upper hand at the time is the one who has the final say,
right,
so to speak, right?
And what's strange is just like, well, like I said, we were all born into this world where these displays of physics in weaponry exist.
Already,
they're not going away, right? We can't unlearn how to put these bombs and these things together. So
I think we've had this conversation before where we're saying like the United States has over 7,000 nuclear warheads, that I'm pretty sure it's over that number. And like you said, the plan isn't disassemble all of these, destroy the knowledge of how to make them. None of that is ever going to happen.
No.
So it's important to understand what kind of weaponry is out there and what it does. Right.
And we have a responsibility to only use these designed weapons in situations that are totally necessary, I think. And I don't know, this is where politics come in, where was this an example of where this needs to be a totally necessary use of a MOAB bomb? I don't know the answer to that, but nonetheless, you have to you can't split your mind up and say, hey, I'm going to be a person who is totally against using this display of force, and you can't be somebody who is just totally in favor of it. We have to tread both lines, right? You have to.
Yeah,
we have to move forward in our minds that these things exist. We have to use them when they're necessary. It's good that we have them, because if we didn't, then people could just walk all over us, right? We would be enslaved to the people who do have them.
And then the last point I wanted to make is that even though it has devastating effects, like it said, it would literally almost turn a person inside out, it pales into comparison to nuclear weapons that we've used in the past in World War II, and completely pales in comparison to the modern nuclear weapons we have now, that we have in our arsenal right now. So as impressive and as insane as this bomb was in its own right, it is still not of the nuclear variety, which is extremely more devastating. And I think the same arguments hold true, even though the physics is different and the scale of it is different. The same sort of philosophical implications apply, right? Where you need to think ahead about the overall picture that we're in, the war, and like you were saying, it needs to be really strategic in the way that you move forward, tiptoeing around these ideas of weapons and which countries are together.
Yeah.
And a few things from the chat that I just saw is that Andy said, I actually think we are closer to understanding how to live without them than ever, but I don't think it will happen in our lifetimes. So that's no reason not to strive for that. That's a good point.
I agree with that too.
Like, yeah, we're getting to the point where we don't need them, but I think the point we were trying to make is that we all know we don't need these weapons, but now that they're there, they're kind of, they're in your arsenal bank, right?
Yeah,
that you're...
and the outliers, I don't know anybody in ISIS directly, but like,
you don't.
Yeah, but for somebody to, in my mind, want to use these weapons that they have against, the ideas of freedom that we've established in our side of the world, to use our display of power to say we're not going to allow that, I think is justifiable to a degree. I don't like the idea of killing ever, but I'm also not a pacifist, right? I think that every once in a while you need to show a display of force to prove that you have it and you are willing to use it, right? That's just my 2 cents on the matter.
Yeah, I kind of agree with that.
Nonetheless, Tom, interesting. I don't think as many people really think about the physics behind weapons like this, and so I thought that was a nice topic to get into.
So usually each week I try and take something that wasn't from the past week's news, but this one sort of gripped me in, and I was reading all about it for the whole week, so I wanted to talk about it.
Definitely. A quick little funny thing to end on, just to lighten the mood a little bit. When I took modern physics in my sophomore year at Stony Brook University, we learned about the development of nuclear weaponry and whatnot, and basically the physics behind it. And one of the questions on my final was just simply, how does a nuclear bomb work? And I wrote, the first sentence I wrote was, a nuclear bomb works very well. And then I went on, obviously, to answer the question, but I thought that was kind of funny.
Yeah.
So with that, guys, that is our show this week.
Yeah, thanks for stopping by.
Thanks for coming in. We hope you enjoyed this. Again, big shout out to Kate Cremens, Dan Smith, your mom, your sister, for the support, both in the way of the graphics and things that we were able to put up this week, and for the financial support. And thank you to everybody in the chat that keeps this show kind of gives it its blood, basically. We really appreciate you guys. We hope that you're enjoying this content, and we can't wait to grow a little bit further. So help us spread the word, and
thanks for all the continued support, guys.
Definitely. With that, we will see you guys next week with episode 12. And
make sure to tag us in any videos or science things you see.
Yeah,
tag us trèSci.
Missing someone is as normal. Missing someone. Missing someone. With all your heart. Missing someone. With heart. How much you miss her. And you deserve. From the start, and you did it right from the start. Missing someone is as normal. Missing someone. Missing someone is as normal. Missing someone. With all your heart. Missing someone. With heart. Missing someone.